Okay, thank you all for your time. So we wanted to get a conversation going between people in networking, optics, hardware, distributed systems. And the main motivation here is actually very simple. It's the fact that this is a time of change. If you look at almost any resource underlying cloud infrastructure, whether it's compute, networking inside the data center or in the long haul, or different kinds of storage, the dominant technology for each of these resources is approaching the tail end of its S-curve. Things are looking like a plateau. For example, if you think about compute, the primary metric of interest is flops per dollar that we can achieve. Thanks to Moore's law and Dennard scaling, we've had a lovely ride over the past 35 years. But because of fundamental physical constraints on the size of transistors, the CPU drive voltage, and the number of cores that we can put on individual sockets, things seem to be flatlining. Now, this has actually prompted a lot of work in custom accelerators, things like FPGAs and GPUs and custom ASICs that are getting a lot of traction in cloud environments. And you probably heard Mark talk about the growth of FPGAs. Later in the session, you'll hear from Tom and Samrama about some of the FPGA innovation happening for networking workloads. Similarly, when you start thinking about the network inside data centers, it relies on electrical switches. And there's an analogous phenomena that I'm terming the Moore's law for networking. Essentially, every couple of years, switch vendors give us a new switch generation that has double the bandwidth, but the cost remains exactly the same. Now, this is a lovely property because it allows us to build faster and faster networks that can keep pace with increasing demand while keeping the overall network cost low and constant. And that's actually one of the assumptions underlying the cloud economic model. However, things could start getting tricky very soon. And to understand that, let's look at this graph again. So historically, the increase in switch bandwidth has come from the fact that we are able to increase the speed of the SerDeses at the edge of the switching ASIC. And the switch vendors have always used the non-return to zero modulation format. So 1 is encoded as high voltage, 0 as low voltage. However, the latest generation of switches is the first generation where we've had to resort to higher order modulation, because it's becoming harder and harder to increase the speed and the density of those I/O pins. So this is like 4-level modulation, which means that you encode 2 bits per symbol, but it means that you have tighter SNR requirements because the levels are getting closer and closer. And this is a trick that's hard to play over and over again, because if you go to 8 levels, your SNR requirements are even harsher. So if you were to step back and look at network inside data centers, the primary metric of interest is the gigabits per dollar. We've had a lovely ride, but within the next 5-6 years, so by the time we get to 50 terabit switch generation, beyond that, things could start to look very dodgy. The same thing applies to other resources. If you look at WAN capacity, we are actually approaching the Shannon capacity of individual fibers. If you go to the next storage session, you'll hear about fundamental physical reasons why we are approaching capacity limits on hard drives. Now, if you are the CTO of a company, this is a nightmare scenario. It's a perfect storm. But for researchers, this is the perfect opportunity, because it means that if we come up with a new technology, no matter how disruptive it is, if it leads to a new growth curve in terms of these metrics of interest, it has a very good chance of deployment. And I think that's a really powerful message. And if that's the only message that you take away from this talk, or even from this session, at least I and Yibo will be delighted. So what I want to do next is talk to you about a little bit about the disruptions happening in the networking space, and tell you about optical innovations that we are doing inside the company, both in research and in Azure networking, to address these challenges. So I'm going to start with the network inside the data centers. And if you remember, I told you about this Moore's law for networking and the fact that that has allowed us to keep the cost of the network low and constant. However, if electrical switches stop scaling for free, we'll have an increase in the cost. And I'll explain the shape of this curve in a couple of slides from now. What's really worrying is the timing of this, because this is expected to happen around the same time where the cloud traffic not only continues to grow, but its pace actually picks up. Because of custom hardware, FPGAs, GPUs, because of new scenarios like large-scale learning, which means that we'll be generating and consuming a lot more data and doing it in a power-efficient fashion. So this is a big problem for us. And one of the benefits of working at a place like Microsoft Research is that we always think of medium-term strategic solutions and long-term disruptive solutions. And I wanted to give you a sense of those sort of examples of those solutions in the context of this problem over the next few slides. So to understand the solution, let's look inside the problem for a second. So if you look at a switch inside the switch, we have a switching ASIC that sits on a substrate or a package connected by BGA connectors or I/O pins, a PCB trace, and an optical transceiver that goes from the bits or the electronic domains to optical domain. So something tiny like this. Now, it is the speed and the density of the I/O pins that's causing the problem because it's harder and harder to scale. And so the obvious thing to do is that, well, why don't we move the optics closer to the switching ASIC, which means that you get rid of this bottleneck resource and the switches are easier to scale. Now, this is something that's been discussed a lot in the optics community, in the silicon photonics space, lots of names to it. We are calling it in-package optics. So essentially, what the switch would look like 2 generations from now is that you'd have a switching ASIC. It would be surrounded by chiplets comprising electrical components, so all the drivers and all the analog components, and then the optical chiplets. And what this would do is it would take the data being generated by the ASIC and modulate light, which is then sent tens or hundreds of meters. Now, in this case, the chiplet is made in silicon because of yield reasons, to reduce costs, and to make it amenable to integration with the CMOS ASIC. And what we've started doing is actually designing our own chips. So this is a silicon-based chip designed at our lab. Is Kai here? He's the chief designer who makes the chips for us that are being fabricated at external foundries. Now, one of the key technical challenges here is that, well, to do optical networking, you need light, and it's hard to generate light in silicon. It's a fundamental problem. It's an indirect bandgap material. So what we now need to do is need to have disaggregated transceivers. Because in a standard transceiver, the laser and the modulator is in the same package. Whereas in this case, we need a separate light source, in this case, which happens to be shared across all the chiplets. And this is cool because it means that we can have a better light source, we can actually cool it better, and I think Dan is going to tell you more about some of the implications of this architectural chain. Now, this is typically made in a material like indium phosphide, and again, we've started designing our own chips, and I think this is an animation that will show you the different layers of the chip. It comprises lasers, waveguides, and other components. I think it's few millimeters by millimeters, Kai, is that?
12 by...
So 12 millimeters by 12 millimeters, and that's going to be shared across the entire switch. Now, this is an example of a medium-term solution, and I want to step back and talk about the implications of this for the overall cloud network cost. So historically, cost has been neutral. We are seeing signs of disturbances, but if we are able to deliver on this in-package optics solution, we'd be able to extend the cost neutrality of switches for the next 5 to 6 years, which is great because it means that the world's not ending. But at some point, we'll run into the actual physical constraints on the number of fibers that we can align at the edge of the switching ASIC, which means that we'll have to have complex solutions and an increase in overall network cost. And at some point, we'll run into the actual CMOS scaling limit, whereby you cannot put more transistors onto the switching ASIC, which means that we'll have multiple ASICs on the same die inside each switch, which in turn means an increase in complexity and an increase in cost for every network generation thereafter. And that's the nightmare scenario for us. And that's where we really, really come in, the long-term opportunity for optics or photonics. So what we really want to do is actually look at these topologies, and instead of using electrical packet switches, replace them with optical circuit switches, something that's been thought a lot about in the optics community and in the network community. Now, one of the advantages of moving away from CMOS components is that you can develop technologies that have a much higher radix, and you can have a much flatter topology. This means that we can offer better performance per dollar because there are fewer transceivers and fewer switches in the network. We can, because there's no buffering inside the network, we can offer very low and very predictable latency. And that predictability is really important for the kinds of application scenarios that we expect to develop in the cloud over the next few years. And finally, because we don't have dependency on CMOS, this can actually be a long-lasting solution. So this has actually motivated us over the past couple of years as a team to develop a research prototype that shows the basic feasibility of achieving very fast optical switching, nanosecond switching, so that we can match the performance of electrical packet switches. So stuff that's done a lot in the optics community, but this is now building a real system out of it. Now, I do want to point out that there's a big difference in a circuit switched architecture and a packet switched architecture. And so there's a long, long way to go to take this from a research prototype with a bunch of wires back in Cambridge to something that can connect an actual data center and run real applications. So just want to check keep the expectations in check. But the IPO technology gives us the space, the 4 to 5 years needed to do that. So I want to change tack now quickly and move outside the data center and give you another example of this sort of hardware, software, network optics co-design. So about 5 years ago, we used to build mega data center facilities, a few 100,000 servers, big land, lots of power. But increasingly, we are finding it hard to find the land and the power and space for such mega facilities. So over the past couple of years, we moved to the regional architecture, where we have many medium-sized data centers, about 100,000 servers in the same metro region, so 80 kilometers, connected by a regional hub. Now, let's think about the implications of this for the underlying network architecture. So in a traditional mega data center, we have the standard class topology. In this case, I'm showing 4 levels. In all our data centers, we use optical cables outside the rack, which means that every switch port needs a transceiver that I'd shown earlier to do the optoelectronic conversion. And this is a great transceiver, so it transmits over a single wavelength. And when we do transmission over the long haul, so when you're going thousands of kilometers, we need a colored transceiver, which is massive, power hungry, and rather heavy. So I can't keep this too long. On the other hand, when you move to the regional architecture, what happens is that, well, yes, you are essentially taking this big block and doing smaller chunks. But your regional link, the one in the red, is actually 80 kilometers. So what this means is that, yes, we can use great transceivers inside the data centers, but now we have to use colored, power-expensive, hungry transceivers, both on the WAN and on the regional links. And this is a nightmare if we were to do this for power and cost and space and all these reasons. So what the Azure networking team did is they actually went out and designed their own transceivers that are customized for the regional environment. This is a colored transceiver that can operate over 80 kilometers. You can see it's exactly the same form factor as the gray transceiver that we use inside the data center. And essentially, the trick is to customize the DSP, to customize the FEC for the particular scenario of interest. If the light's not going tens of thousands of kilometers, why would we do chromatic dispersion for that distance? So those are the kinds of designing for our scenarios that led to this innovation. And this was co-designed both inside the company and working with Inphi, who manufactures these transceivers. And these are being deployed in our data centers over the past year. So the reason I chose these 2 examples is to give you a sense of our thinking. Innovation by combining optics with networking, distributed systems, architecture, and hardware. And we genuinely believe that to develop the next generation of cloud infrastructure, we will have to innovate across the stack. And we can do this because as a cloud operator, we own and operate the entire stack. As I showed you, we are developing our own custom chips. We are building optical components. We have designed and are deploying our own transceivers and our own switches. And as you'll hear, we already have our NICs. So we can deploy things on the stack, on the NIC, or the servers themselves, which allows us to innovate across the stack. And that's something that we're doing both in our work, but also in all our collaborations with cabinet collaborators. For example, the work that we are doing with Dan and many of you in this room. So that's the message I wanted to get across. Thank you for your time. I think I'm running out of time, so thanks again. Yibo, do we have time for a question?
Yeah, maybe let's take one or two.
Yeah, so real fast. You didn't say anything about efficient use of the optical network, but even with 100 megabits, 100 gigabit right now, we're seeing that people are doing small writes, and not many of the data lanes on this sort of wide data path are really occupied. So you've got, you know, say 10 data lanes, 66 bits each, and you've got 1 byte of good data there,
Yeah.
maybe 60 bytes of headers, and the rest is just empty. What can be done at that layer?
That's a very good question. I'll give you 2 short answers to that question. You could apply that question in the WAN scenario, where efficiency is very important, and you really need to think about software-defined primitives to achieve that. I think your question is more in the intra-DC context. And one of the interesting things about the intra-DC context is that things like the 60-byte header or the 40-byte header come from scenarios if we are limited to legacy protocols. If we control things like the NIC and the underlying network, in many customized scenarios like RDMA clusters, I would argue we should just go to customized protocols that reduce a lot of this overhead.
Well, aren't we also going to have to dynamically allocate the data lanes? I mean, if somebody's generating 1 byte at a time,
Yeah, I completely agree. I think in that sense, you really need a decoupling of the data plane and the control plane, which allow you to make those changes. Yes, I completely agree on that front. Do we have one question? Time for one more?
Maybe let's bring the questions offline.
Okay.
Yeah. All right. So let's thank Hitesh again.
Thank you.
So the next speaker is Tom Anderson. I believe most of you already know him, but here's a short description. Tom Anderson is the chair in the Paul Allen School for Computer Science Engineering at UW. His research interests span all aspects of building practical, robust, and efficient computer systems. So he's a member of National Academy of Engineering and the winner of multiple Lifetime Achievement Awards. So.
Great. And I think actually this will be this great counterpoint. I think there are, I'm actually at essence an operating systems person. And many of the things that have been driving our research over time is just this recognition that we are in the cloud setting spending, or particularly for really key applications, spending huge amounts of time just doing these repetitive operations in the operating system. And what's clear about the hardware technology trends are that everything that can be re-implemented, everything that's of high capacity, the things that you're doing all the time, are going to be re-implemented in hardware. You can't afford to do just general purpose processing for things that you're doing many, many times. You can see this with TPUs, but you're also going to see this on networking and for operating systems. So essentially the argument that I'm going to try to make here, what we've been looking at is on the protocol stack, but more broadly, I think one could ask this question more generally about operating systems in general. So if you look at how, I'm going to come down from the application side rather than up from what we can do in hardware. So one of the things that's really characteristic of these applications is, of the applications people actually run in data centers, is that large amounts of very fine-grained communication, partly just because as you start to spread applications out over more and more nodes, because you need more and more nodes because Dennard scaling isn't doing it for you, now your communication granularity goes down. And kind of an interesting data set that somebody in the SIGCOMM community collected all of the RPCs inside of the Google data center over a period of time, that the median size of that was only 300 bytes. So generally, you're doing single packet transfers between nodes. You still want the semantics of TCP, so that is reliable in order delivery. It's many to many. So what you would think it's like the applications that this drives for are key value stores, databases, distributed analytics, and that you're pushing performance limits on those and then scaling up as you go. So the question is how you can deal with this. So on the software processing side, Linux even if you kind of ignore the VM layer because you're going to say Catapult will take care of that for you. On the VM side, or on the TCP side, you're spending huge amounts of time doing just regular processing. Just if you're trying to do through Linux, about 3.5 microseconds per packet. And then single core performance is not going to bail you out. So you could try to parallelize this, that is, try to run many connections over many cores, but potentially that's going to just end up burning lots of power and spending a lot of effort, a lot of cost and time doing things that you don't really need to do. So there are lots of proposed solutions to this. Probably everybody in the room would know many of these. So one of them is kernel bypass, so DPDK or things like that. The challenge, though, is that what you want is something that's going to give you policy enforcement. That is, if you're in a multi-tenant data center, you also need to worry about, well, what are these applications actually doing, and can you trust them? Is it going to be the case that they're going to obey congestion control? Your behavior of your network is going to depend on end host behavior. So you need something that's going to give you policy enforcement. Some people are deploying SmartNICs or NIC CPU arrays. And I should say, actually, there's this really nice paper from MSR that Sambra is possibly going to talk about, I'm not sure, that actually goes through essentially a lot of the same arguments and that appeared at the last NSDI 18 and actually makes all of the same arguments that we would make. So if you try to put on your NIC essentially CPU arrays, the challenge for that is there is this complicated thing as you scale out the number of CPUs you're doing your TCP processing, that you have this complex assignment problem of that to the CPU array, and limited per flow performance. That is, if you potentially want really high bandwidth for a given individual flow. And it's also relatively expensive to go build those. RDMA is the one that the research community is spending most of their time on. In fact, most of the stuff that I'm going to talk about here is essentially trying to understand how you would build a more flexible RDMA engine. RDMA, the API is fine for some things, but certainly for these kind of small scale, single packet RPC communication, as a protocol, writing or reading from memory isn't necessarily the natural thing that you would do if you wanted to build a really fast RPC system. And then the hardware for RDMA actually bundles not so well with the congestion control protocols that you would actually want to use in practice. So some people have also done TCP offload engines to be an example. You need, there's going to be an argument they're going to make towards protocol agility. So ultimately, if it kind of integrate over that whole set, I think what you want is the traditional operating system functionality. That is the feature set of operating systems, which is multi-tenant isolation, the ability to say that the behavior of applications doesn't affect other applications, and at the same time, hardware assist. That is some way of doing a flexible, reconfigurable architecture so that you could then change your protocols as you need them, do policy compliance as you want, scale up connections to really large numbers of connections, CPU efficiency in the common case, and performance efficiency. So essentially, you would think of, you want the flexibility side to be able to do whatever you want, and the other side be able to handle the stuff at the speeds that you want to handle them without having to do a huge amount. And I'm going to make this argument independently of the FPGA versus VLSI argument. Microsoft has its own perspective on this, which is FPGAs are the future, but in some ways, the argument I'm going to make here is going to be independent of that. So you can think of this hardware assist at multiple levels. So one layer, and the keynote talked about it to some of this extent, which Microsoft has already deployed, widely demonstrated, that is if you're only asking about the packet processing at the VM layer, that is creating a virtual network that that makes the virtual machine look like, oh, okay, I've got my own little LAN here that I'm going to be able to communicate with. That set of work is pretty regular and actually pretty demonstrable that you can move that onto hardware. What I'm going to end up talking about is a harder problem, which is, okay, now once you've gotten these packets to the virtual machine, The virtual machine's now spending almost all of its time doing TCP packet processing in the guest operating system. So that's inefficient from the customer perspective. It's like, why was I burning all this CPU time for that? So can you take and try to do hardware acceleration, or flexible hardware acceleration inside the VM? So how you do TCP packet processing in hardware. And then you could ask the similar question about the application level processing. So you're handing this off to an application. It's also doing essentially layer 7 packet processing. How do you want to try to optimize that? This whole set of things can actually be handled in this thing that I'm going to talk called FlexNIC, but it's just a model for how you would do the programming for it. And then I'm also going to talk a little bit about how you could do this flexibility at network switches. And in general, where this is going to tie in with the optical side is where you do have congestion, that is where you have large amounts of communication coming in. Generally at the top of rack switch or whatever, you are going to need to be able to do something on the level of trying to do resource allocation in some fashion, largely in the kind of programmable space. Okay, the overarching lesson here is going to be that common case packet handling is systolic, which is to say that individual packet, the steps that you're taking to do packet processing is regularizable, and that can be pipelined, not just packet to packet, but even within a packet that you can do kind of regular communication. And as a consequence of that you will end up being able to do large amounts of, high bandwidth operations even on a single flow because you're pipelining individual stages of computation. And I'll come back to this point that I made earlier, which is that anything that can be regularized and you're spending a lot of time on will eventually be built into hardware. It's just how the economics of data centers is going to work. So now the question is how you can go about this. And this will happen both on NICs and switches. Okay, so the programming model we started with is essentially reconfigurable multi-stage pipelines. We're not the only people working in this space. You take this packet stream coming in, you have a programmable parser that goes through some number of stages of computation. These computational stages are protocol agnostic. You can run essentially about a terabit per second in a single pipeline. Barefoot's demonstrated that. So from a NIC perspective, that is from an end host perspective, that's pretty good. That'll carry you pretty far. And the idea is going to have predictable performance. The stages all execute in parallel. You can think of essentially each successive packet goes through the stage in the sequence. As a consequence, from a single flow perspective, you're still processing everything in order, as opposed to spreading it out over multiple pipelines or multiple CPUs, which you might be doing in a SmartNIC operation. Then you're having to make sure that all of the packets for a given flow go through the same sequence or on the same processor, just for kind of state management and ordering constraints. Okay, so what do these match action systems do? You can think of them kind of the simple cases that they can steer packets, they can initiate DMA, trigger replies or whatever. They're just doing some kind of simple, this is an application that's trying to write on a particular port, then what I should do with this is to hash it to a particular core and then DMA to a queue or something like that. That because they're regular, again, in a systolic model, you don't want loops. There's no complicated arithmetic. You have to be careful about what you're doing with state. You can't have an arbitrary number of stages. It's not programming the way we would normally think of it. Rather, you're programming kind of for hardware. And so we built, kind of designed a part of this from a kind of NIC perspective. How you would actually make this work is you actually, for the NIC, actually has multiple pipelines coming in. So it has data coming in for received data. That is, you're having to do some set of pipeline stages for packets that are arriving from the network. Similarly, the host itself is also delivering packets into the NIC. So we have some pipeline for handling that. There's a transmit pipeline to actually send data out. There's also a pipeline to try to do essentially programmable NIC behavior. You can kind of imagine if you were to try to decompose what happens on an RDMA packet if you're coming, like if that was your protocol that you were trying to implement. What happens on an RDMA packet is that you're essentially you're parsing the packet and then demuxing on an element of the packet to tell the DMA engine to do a particular operation. That step is something that's pretty similar to what a TCP packet does when you arrive. Like, oh, okay, I'm going to get this packet in, and I want to decide which queue this is going to go into based on the port number. And then based on that, I'm going to, and maybe the sequence number in the packet. And then that's going to tell me where to go from there. So what this then allows me to do is to do this, transform these packets efficiently in software, DMA directly in and out of application data structures, so it looks like it's just has all the same benefits that RDMA has, and then send acknowledgments out on the NIC. But potentially you could implement TCP with it. So if you look at what TCP is doing, it's got a lot going on, right? You're opening codes and connections, you've got locking on socket API, you've got IP routing, ARP firewalls, like congestion control, like very complicated connection state. Often in the kernel, if you look at the kernel code, you're doing multiple steps. You're chasing data structures, you're doing pointer chasing. A lot of it's like, oh, okay, how is this going to end up working in this kind of systolic model? And the model we've taken is one that would take and essentially split out the operating system code into kind of a fast path that's regularizable, and then a slow path for everything that's not regularizable. And then hopefully you could say, oh, okay, the slow path just handles offline. So you can think essentially of the fast path doing all of the normal operations you would do on every data packet, generating data segments, applying rate limits and so forth, collecting congestion statistics, all of this ending up running on the NIC itself. And then the slow path running in the kernel that handles essentially all the other kind of essentially connection or control plane operations. And then the application ends up doing some additional amount of work. One of the aspects of this is to say that you're splitting up congestion control in a way that splits the work so that instead of thinking that you're doing congestion control in every packet, you can think that you're doing it on a kind of round trip basis. So collecting information on the data path and then using it on a kind of background basis to enforce congestion control. But that's actually sufficient for implementing the protocols that we have. So this is a kind of performance graph. Maybe I'll end up leaving here, which is essentially how well this can do. The yellow, this is Linux here, scaling up to 16 cores, not very well. And then a software implementation of what I've just described, which actually does enforce congestion control, compared to a software version of just a DDPK TCP version that doesn't enforce congestion control. They actually do reasonably well. And then the kind of hardware version is that line over there. All of this is actually just emulated rather than other. I'll just briefly talk about, you can actually think about a bunch of these issues also happening inside of the network itself. So switches themselves can also be programmable. And you could ask this question of what can we do inside of the network using reprogrammable hardware to do different things. And one of the things that we've been looking at is to do essentially approximate fair queuing. So fair queuing is one of these things that is kind of longstanding, maybe 30, 40 years ago. I'm not actually sure exactly when it was. 30? 30 years ago, okay. So I think it was like dated from almost before I graduated from grad school, so that's like how long ago it was. But the idea is that you get isolation, that is more predictable behavior out of your network if you're able to say that if your queuing discipline and how you handle packets inside of the network obeys fair queuing. The challenge for it is that it's really difficult to implement these things in any kind of fashion. This is just an animation of what happens as you go about do this. In order to get fair queuing to work, and I'll just go forward from this, the different pieces, you need to have a sorted packet buffer. You need to store and update per flow counters. You need to track a global state that updates on every packet. And all of that ends up like, oh, okay, how are you going to end up implementing that at multi-gigabit speeds? We were talking about trying to implement it at many gigabits. So the argument that, is that you could potentially use this kind of reconfigurable match action model to simulate fair queuing or approximate fair queuing. And I'm not going to actually do the example here, but I'll just skip by it. But the idea is basically to use multiple queues to try to approximate the behavior, store approximate per flow counters in tables and so forth. So there's a lot of kind of research that people are doing in terms of trying to understand what you can do with reprogrammable switches. And the outcome of this ends up being, so this table here, this is actually flow size on the x-axis, and then normalized completion time on the y-axis, so small is better, and then AFQ, which is the blue line. So as you get bigger flows, then of course it takes longer to complete. But one of the things that you end up seeing is even for things like TCP, which is kind of the best known congestion control protocol for data centers, you can do better as a consequence of having more intelligence happening inside of the switch. Okay, and I'll just leave it there.
Right. Thank you.
Thanks. Yes, that's summary. Yep.
Any questions?
Cool.
So I have one.
Oh, okay.
So you talk about Flex TCP. So is it, sorry, maybe I missed it. Is it a totally kernel bypass technique, or is it still accelerating the kernel stack using the hardware?
The enforcement, you can think of it as the equivalent of virtual. I think probably the best analogy for this is there was a period about 40 or 50 years ago where we decided that what we needed to do for multi-programming was to have virtual memory hardware. And there was a period where people didn't know what that virtual memory hardware looked like. Like, what exactly were the abstractions? What we ended up with was this notion of having essentially table-driven enforcement mechanism that's controlled by the operating system kernel. That model is essentially the one that we're moving towards, which is we're trying to come up with some new set of constraints, some new model for how operating systems are going to interact with networks. That's going to be, okay, this control plane's operating in the kernel. That's the enforcement mechanism. It says, here's how much bandwidth you're going to get on a particular flow. Here's the logic of what you're able to do from an application perspective. And then everything else, what the application actually does itself is all done at full speed. And so what VM hardware does essentially is to say, look, in the normal case, you're executing at the full speed of the hardware, even though I'm providing this kind of protection layer with some hardware assist. And the question that we're ending up trying to figure out is, what is that hardware assist that you need to be able to implement this at full speed?
Okay. Right. Yeah.
Okay.
Yeah.
Oh, that's someone.
Oh, sorry. Did you?
Can we pass the
Ken,
microphone?
did you want?
I have the microphone.
Yeah.
So I'll ask my question anyway. So a lot of dialogue about RDMA centers on NIC use of resources that are really living in the OS, such as the page table entries and actually the specific DMA mappings, and then the DMA permissions records, which are all tables. But then this starts to exceed the amount of SRAM available, and most of these NICs don't have time to go off to DRAM on an average packet. Do you have an opinion on all that? I mean, where's that trending?
Yeah, so I think Sandra, so like if you wanted to start coming up, there was a really nice, again, this NSDI paper of looking at how they map Catapult. They have a two-level connection state model where the SRAM is for the active connections, and then they have a DRAM backup for other ones. I think once you start to think that your operating system is managing hundreds of thousands of packets, you're needing to do some kind of two-stage model for it. So I think that also is a really interesting question of, well, if everybody is actively using, say, tens of thousands or hundreds of thousands of packets of connections simultaneously, then does this kind of caching model work? And how do you make that work? Now, the upside is that even if you have to fetch your data in from into DRAM, your connection state in from DRAM to do some work, it's still, as long as it's relatively compact, the only amount of, the thing that you might be doing over time would be some regular amount of operation. The amount of time that a connection is actually actively using the NIC is going to be relatively small. So the only number of active connections you might be doing inside the NIC at any point in time might not be large. There are also large amounts of just regular protocol issues that come from trying to run large numbers of connections simultaneously. Like TCP is just basically broken for once you get above 1,000 connections. We ran a really simple test that just doing simple RPCs between two nodes with 1,000 connections, and Linux will actually literally starve connections. Like, just like, oh, okay, is that the best we can do? Like, hopefully not. Okay, great.
It's time for a last question.
Oh, a last
Sorry,
question.
just a quick question.
Yeah,
So, I mean,
quick one.
what you're proposing with FlexNIC looks a lot like P4. Are you trying to use the same programming abstraction of P4 at the host side?
So you can think of it very similar to P4. I think the difference is P4 doesn't really have a model for how to program DMA.
Right.
And so we added essentially, it's P4 plus the kind of DMA programming.
Okay, thank you.
Okay, let's thank Tom again. So the next speaker is Sambrama Mankar. She is a technical lead in Azure networking, working in the area of accelerated networking. So at Microsoft, she has primarily worked on network offloading technologies, especially in the area of network virtualization, such as virtual machine queues, single root SROT, and generic flow table offloading. So,
thank you. Hi, like he said, my name is Sambrama. I'm a tech lead in Azure networking. I specifically work in the host networking group. And for the last couple of years, what we've been working on is to offload the software stack that we have in the Azure host to an FPGA, SmartNIC, and deploying this entirely in our Azure data centers and seeing great benefits out of it in performance and latency, throughput per packets per second, et cetera. So I'll go into some of the details about how we went about implementing this. So the agenda for my talk will be a little bit about the Azure background, how the problems that we have in scale, and the SDN stack, the way it's implemented today in the software stack, and what are some of the challenges we face around that and in packet processing at a per packet level in the host. And we'll also talk about what are the considerations we employed to determine that FPGA SmartNIC is the right choice for us to go forward. And then I'll go into some of the details of the architecture and the design of the SmartNIC. And then we have a lot of lessons learned because this is pretty much the first time where we are deploying at such a scale software hardware project coexistence and deploying hardware at such a scale to be able to debug it, monitor it, have alerts, and at an agile way where we, which is like our cornerstone of Azure and networking. So this is the generic slide that we use for the Azure services. So we have at the bottommost layer the infrastructure service, which includes our storage, compute, networking, et cetera. And on top of it, we have the data services and providing the app services like Azure ML, analytics, et cetera. So Azure and networking has come a long way since it was first deployed. From in terms of compute, we have started from like 10K or 100K VMs, and now we are at millions of virtual machines. And Azure storage has seen the same rate of growth as well as the networking, where we are seeing from terabytes of data to petabytes today. So this is a generic marketing slide that we use, and we see at what rate the Azure is growing on a day-to-day basis, literally. We have to have support for all the Linux VMs because most of the virtual machines that are out there are Linux VMs. And we see a great growth in terms of the deployment, onboarding of new customers, and the different kind of features and requirements that we have in terms of Azure and networking specifically as well. So that would kind of show us like the agility that we need to maintain, because a lot of the features that we add are customer driven, either through issues that they face or the new features that they need to move from their current model on-prem network to the Azure network. So other ways to think about scale. So it's not just about deploying this service or deploying a feature. It's about how do we handle failures, how do we detect, monitor, and it's a continuous feedback loop that we need to be in. And believe me, we often get our on-call rotations, and it's not pretty to live through 1 week of an on-call rotation, because if you don't have a backup of knowing how to automate this detection of hard failures like switch, link, rethink, node failures, the crashing of any software components in the nodes, etc. We need, at such a large scale, it's impossible to do, literally impossible to do manually, or even not having a super sophisticated automated solution for that. So we have, and another customer goal would be to actually, one is detection of these failures and mitigation of it. So most likely we would prefer to know about an issue before a customer even notices it. So we need to have the automation in place to detect these conditions that are going on, some hard failures, and be able to mitigate it, which would be like service heal the virtual machine to a different node, or in our case, for example, switch back from, let's say, if the hardware is misbehaving, switch back to the software path, etc. And then we always have the problem of soft failures, which are not obvious. Obviously, if the link is down between two switches, it's easy to detect, easy to fix. But if there are soft failures that we see very often, is like 1 in like 100 packets is getting corrupted by 1 extra byte or something like that. And those sometimes I've seen even in practice, those go unnoticed until for example, in our case, when we offloaded this flow to an FPGA, the FPGA was adding an extra 32 bytes at the end of the packet, and that went unnoticed until some TLS type of checksum was happening, and then at the customer endpoint, they would see an effect of this. So how do we detect these kind of failures? And a lot of issues that we see are in latency. So generally, everything is working fine. Occasionally, the latency peaks at 50 milliseconds or something like that in a TC ping type of operation. So how do we detect that? How do we monitor that at that scale? That's also very important. So I think, again, like I'm stressing, the automation is the key for all this. The other thing is the IaaS customers, they are highly intolerant to any virtual machine downtime or any networking downtime. So whenever we have to service any of our components, and we have a lot of components, including in the host, in the virtual machine, in the host, and now in the hardware, etc., the serviceability is the key. We cannot afford to bring down the host. We cannot reboot, so we try to update all our components rebootlessly, except for the OS, which also we try to do it in such a fashion that the downtime is extremely less. Any networking components being updated or being serviced need to guarantee that we do not see a network outage to the virtual machine. And we try our best to actually keep the TCP connections alive. So that's the goal of it. Basically, the VM should not really be able to see a TCP connection drop. So the key to this is performance. Everything is measured at like 4 to 5 nines on a customer basis, which includes the performance, the network performance, the host performance, the availability, the VM availability, whether they should not suffer any kind of downtime, and the serviceability of all our components. So how do we achieve SDN in Azure? So today what we do is what we call as the host SDN. So our data plane runs in the host. We have distributed controllers that are running across the region. So for example, the SLB has a regional SLB manager. For any VNet programming, there is a regional network manager, etc., that is per region. And we have controllers running in each of the hosts. So any of the configuration that comes along from the management plane, which is using the REST API like a portal or command CLI, however the deployment occurs for the virtual machine, that comes to the regional network manager eventually. And those policies are programmed to a per host level. And so the controller on the host programs our virtual switch that runs in the host, and the data plane in the virtual switch is which applies the policies. So obviously, then you have this data plane needs to apply the per flow policy to millions of VMs, and that's only achievable because we are handling it at the host level for whatever number of VMs that are running on the host. So this is a diagram of our software stack. This runs in each of the hosts. So we have the virtual machines hosted on the Azure node, or the host as we call it. So before hardware acceleration, what is presented to the virtual machine is a synthetic NIC or a software NIC. Any packet that needs to come in and out of the VM is always going through the software stack in the VM. That goes through the hypervisor to the host. And in the host, we have what we call as a VM switch, which is a layer 2 switch, which basically is really a delivery mechanism in and out of the VM. And all the policies that I told that get applied to the controllers, the controller programs using a VFP API, which is a simple match action and match action table API. So that the controllers program the VFP with that information. So like I said, there could be different kinds of controllers, like something for load balancing, something for VNet customer address to the provider address mapping, ACLs, metering, etc. So each of the controllers can program their own rules, and those go into different layers of VFP, and they're independent of each other. So if we were to add a new feature, we could have a new layer, and none of the other controllers would have to change any of their policy. So in VFP, what would happen is, let's take an example of a packet being transmitted from the VM. That would land from the VM over what we call as a virtual machine bus to the host from the hypervisor. And in the host, when it hits the VM switch, VFP is built as an extension to VM switch. So originally, when we started Azure, all of the policy enforcement was done as part of VM switch. And then due to different constraints, because you will the VM switch update requires a reboot, etc. So we went with this model of having a pluggable virtual filtering platform within VM switch. So every packet that VM switch sees in inbound and outbound path is routed through VFP. And VFP is the one that is the brains of the host SDN on the host. So it applies all the policies. It goes through the layers. For example, on an outbound packet, it would go through the ACL layer, modify the packet based on the configuration, go to the VNet layer, modify that packet, let's say map the CA to the PA. And this might also need some communication to the regional control plane. For example, you might not have the mapping of this destination VM. You might need to wait for that configuration to come back and then apply that change to that packet, and then go to the SLB layer, so any VIP to DIP mapping would occur there. So this processing allows us to do multiple layers independent of different kind of controllers programming it. Then we go one step further than this, that once this packet goes through it, if you see a connection setup packet, like in the case of TCP, it being the SYN packet, you know that this is a packet and these are the flow ID for this packet, and the end result is always going to be the same. So ACL, VNet, SLB, the NAT layer, combine it, and what is the final action that is called as a transposition, we can save that information so that you don't have to go through the individual layers after the connection setup is done. So we call this technology called as a unified flow, which is actually the basis for our offloading to the accelerated NICs. Yeah, so basically, so this again explains how we would go through the layering. Occur both in the inbound and the outbound. So the VFP is also the forwarder. So once it does the outbound processing for a packet, it forwards a packet, determines the target, and then does the inbound processing based on the rule setup for that port. So the target could either be another VM on the same host, for example, if they were to do VM to VM, and we are seeing more of this in particular requirements, or it could be another VM on a VNet in Azure within the region or another region, or it could be some internet endpoint. So it doesn't matter. Basically, the VFP is just doing a per port policy application on inbound and outbound. This just shows you the flow of a packet. So for example, the ACLs would be applied. The different action is specified for that layer. For example, drop certain packets with 10.416 address, etc. And then the action at the load balancer layer, and then the VNAT mapping would occur at the end layer. So what do we see as the challenges in this, right? This works fine at 1G, at 10G, it works fine. But what do we see as challenges? As the networking speed increases, there are more and more packets being generated, but there's not enough CPU to handle this load. So what are the options for us? So we would prefer to offload this to hardware. But when we offload it to hardware using ASICs, you are having a 1 or 2 years of cycle to update the ASICs. It might not be sufficient. What are the features available in the ASICs, etc. So we have to go with, we decided to look at FPGAs to solve this problem. So what we have is today we still have the ASIC NIC that provides the access to the virtual machine. There is a technology called single root IO virtualization, which allows the virtual functions, PCI virtual function, to be exposed to the VM. So the packets from the VM can directly access the network to and from it. But if we did that, then it would be bypassing the host, and there would be nobody applying the policies. So we go with this bump in the wire model that the delivery of the packets and reception of the packets from the VM still occurs on the virtual function and the existing NIC. And any of the offloads that the NIC can provide, for example, receive side scaling like CPU steering, task offloads like checksum, etc., or large sum offload, that can still occur at that NIC. But the policy application on a per packet basis occurs on an FPGA that's programmed by our VFP. And we use this API called the GFT API, which converts the unified flow that we talked about in the VFP to the settings, basically what the FPGA understands. And these are some of the measurements that we got from running regular open source tools like iPerf and SOCPerf. And you see, I'll just go quickly over this, is like you see the compute D series gets up to 25G, and we see improvements in the latency, especially because we have SRI, we totally bypass the host stack. So we see per packet per second improvement. And then you obviously also reduce jitter because you don't have any software issues of getting descheduled by hypervisor to run VM processing, etc. So this gives us more cores for the VM processing, offloads all the network to the hardware. And then since the VM can get near native performance, we can also include other workloads that needed that kind of performance. So this is an example of what, on the left side, you have how the packets transmission and reception looks like in the case where it's being processed by the software. So anything coming out of the VM goes to the virtual switch, does the processing, then goes out on the physical layer. But in the case of accelerated networking, it just goes to the network card and directly out to the TOR and beyond. So this is an example of how the GFT actually does the processing. So like I said, the controllers program VFP as today. There's no change over there. VFP still needs to be there in the path of what we call as exception packets, which is the connection setup packets. And for TCP, it is SYN-ACK packets. For UDP, it's the first packet that we see. So we are right now offloading just TCP and UDP, and potentially we would do RDMA flows as well. So like I said, the unified flow gets created in the VFP when it does receive the first packet. So it goes through the slow path processing across each layers, generates this unified flow, which is this is a flow and this is the action. And that is what it configures to the GFT. So when GFT is the engine running inside the FPGA SmartNIC. So when FPGA receives this packet from the VM, let's say an outbound packet, it goes through its table. There's a multi-layer hash table lookup. So like he was saying on the SRAM, and then we have an L1 cache, and you don't find the packet, go to the DRAM, look up that. And if you don't find that packet or a flow for that particular packet, that's tagged as an exception packet and sent to the host stack for VFP to process. And if it does find the packet, which is when VFP offloads this flow, then it does the transformation itself, bypasses the stack, and sends it out on the TOR. Similarly, if you receive a packet, the same mechanism happens, but when it will indicate the packet to the ASIC NIC, which is using the SRIOV and directly indicating the packet to VM, again, we bypass the host. One of the key thing for this is serviceability. So serviceability is a key is because we need to be able to update any of the components without any kind of downtime for the VM, because we have to, So I have just 1 minute, so I'll quickly go over some of the lessons we learned in this area as well. So one of that is basically if the VM cannot suffer downtime, then we need to have a failover, simple failover from the hardware to the software path when any of the key components are being serviced. And so that was one of the key things that we did as part of the initial design, because we also need to service, because the whole idea of using FPGA is to be innovate as fast as we can, which means like our goal is to service the entire stack every month in a sprint fashion, right? So some of the lessons that we learned is, I would say most important is monitoring is really the key. It's not on my bullet points here, but monitoring is the key, because at this scale, when you see generally in hardware, we tend to think that, okay, you need to get a repro. All that's not going to happen, right? Like customers facing this issue, you got to figure it out. So we need to have as much as monitoring alerts and notifications that we can have. The failure rate has remained quite low, and we have some alerts for that, like DRAM failing over some time, or some of the parts that like oscillators and stuff like that failing. So we're kind of monitoring that, like what the thing is for that. And I think another thing is like it's a mindset change as well, because to work in a coexistent fashion between hardware engineers and software engineers, to build a team around that had like initial challenges to understand each other, etc. And that is an iterative problem that we have to solve. And the biggest like benefit that I saw of this one on first hand is basically when we have a new SDN feature that we want to implement in the software. Earlier, when we started off, the software existed, and we figured out how to offload the stuff to hardware. So that's the way we were thinking. But now, whenever we are doing a software feature, we say, okay, how is hardware able to support it? Because we do have hardware limitations in terms of tables, etc. So that is also another like a mind shift that we see while doing this entire project. So that's it. Any questions? Or I don't know if we have time.
I have a question here.
Yeah.
Yeah, I had a quick question about migration. It seemed like there's a lot of dependency on the hardware and whatnot.
Yeah, so like live migration?
Yes.
Yes, so we do take that into account, and that does mean at this point of time to upload the flows from the hardware to the software, because we need to save the state of the VM as it is and then migrate it out. So we will remove the hardware offloads at that point of time, save the state, move it, and then re-enable the hardware offloads in the destination. Yeah?
Do you anticipate there to be any scalability limits with FPGAs as we scale to even faster end host networking, say 400 gigabits per second, maybe even 800 gigabits per second?
Yeah, we do see that. Actually, at this point of time, the bottleneck is the host, because we still have to do the first packet processing in the host. So once the offloads have been offloaded to the hardware, it is still able to scale at that level. But we make continuous improvements. For example, you have the you also have a memory constraint, which is also a bottleneck in that thing, right? Because you have multiple flows. You started out with a single full-size VM, and then you go down to having multiple flows. There is a limit at the end of it. And if any packet has to get processed in the host because of hardware limits, that is a problem that we have to look at. Yeah.
Yes, I guess a follow-on question. Do programmable ASIC switches like the barefoot switches have the capability to handle all the layers here and also hit the cost point as an alternative when the bandwidths scale up?
Right. So, do you have a question? I thought you said.
I was asking if the switches like the barefoot switches, the programmable ASIC switches, have the capabilities to handle this as they scale up in capacity too?
I'm not aware, but the one thing is we are doing all this in the host, so that is something that we have to keep in mind. Like we have to support the host SDN because that's where we try to do all the policy enforcement. Done or done? Done. Yeah, thank you. You can follow up.